Good?
Yep.
Alright, so if we start out with the number 1, and then we make another row with 1s, and we start making new rows, kind of like we do with Fibonacci, but we'll start with a 1, and then we add the numbers here to get the number in between them and underneath. So 1 plus 1 is 2, and then we'll put another 1 at the end. Start with another 1, 1 plus 2 is...
Cool, 0.
3. Wow, guys. Okay, 2 plus 1...
3. I thought it was a rhetorical question.
No, it's not a rhetorical question.
1.
The fact that it's not a rhetorical question is insulting.
6. 4.
5, 10, 10, 5.
Pi.
And it's going to repeat.
Pi. Yep. 6, 15, 20, 15, 6. 7. Oh dear. 21. Then that's 35. Then 35. 21. 7. 1.
Okay.
What about the next one?
Oh my goodness. You'll just have to borrow my program.
Yeah. And Pascal's triangle is cool to look at, I think, but more than that, there's actually a lot of uses for it. It came up by a guy named Pascal. I'm sure Mr. Tilly could tell you all sorts of stories about him. I think he was the one that got his tooth pulled without anesthetic.
Oh.
Okay. One thing that's kind of cool about it is we're going to call this row 1. Row 0. Row 1. Row 2. Row 3.
Oh, they're
4.
2 to the row.
6, 7. And yeah, you just said it. The second number in the pattern is going to be the same as the row number, which is good to know so you can always check yourself. And then another one is, let's say we raise 2 to the power, sorry, no, I just gave away the secret, sorry guys. Alright, add everything in the rows. So we're going to have 1, and 1 plus 1 is 2, 1 plus 2 plus 1 is 4, 1 plus 3 plus 3 plus 1 is 8.
16.
Look familiar? 16. Then what's the next one?
32.
Next one?
64.
128.
Good. These are
256.
Oh my.
512.
These are powers of 2.
2024.
And these are powers of 2, and they are to the power of the row number. So the sums of the rows are powers of 2. I think Josh and I were trying to prove that one time, but I forget how we did it. Oh yeah, if you multiply, what's 11 to the 0 power?
1.
1.
What's 11 to the first power?
11. Oh my god.
What's 11 to the second power?
121.
No way.
11 to the third power?
1,331.
That's ridiculous.
11 to the fourth power?
14,641.
Unfortunately, it doesn't work after that because these are double digits, so it's going to carry and add. So. But
that's so cool.
Okay.
We're gonna have to figure out how, Ben.
Look at this diagonal.
Whoa.
1, 2, 3, 4, 5, 6, 7.
Mm-hmm.
Well, it does make sense because it's the row number, right?
And then look at this diagonal. 1 plus 3 is 4. 3 plus 6 is 9. 6 plus 10 is 16. 10 plus 15 is 25. What do these remind you of?
So, wait a second. Oh, it's the squares.
Yep.
X squared.
Add adjacent numbers in this diagonal, and you get square numbers every time.
Whoa. That was not sarcastic.
What about the
that is sincere.
expanding?
If you have a number, well, not a number, it's called a binomial. A plus b to a power of n. If we raise it to the 0 power, it's going to be 1.
What?
If we raise it to the 1 power, it's going to be
A plus b.
1a plus
1b.
If we raise it to the second power, it's going to be
1a
squared plus 2ab
AB
plus 1b squared. How about we'll just get to something cool like the fourth row. It's gonna be 1.
1a to the fourth, 4a to the third b, then 6a squared b squared, then 4ab cubed, and then 1b to the fourth.
Now you can do this, or you could do this and FOIL it, and then FOIL it, and then FOIL it.
Oh.
If you'd like. That would be easy, right? No, it's not. It's going to take you forever. So the Pascal's triangle is most often taught in curriculums as your ability to be able to expand these things super quick and super fast. In fact, anytime I square something, if it's x plus 2 squared, I don't think, oh, I can FOIL that. I think it's going to be x squared plus 2 times x, which is 4.
Oh, that'll help with what we just did today.
Plus 2 squared, which is 4. So it's, and you use that definition to actually prove the definition of derivative.
And,
in statistics, or probability more likely, there's a...
Yeah, and you by derivative you mean the power rule, or well,
Yeah.
it's used in the, or at least it was used in my proof of the power rules.
Right. Well, actually, it's using the definition of derivative too, I think.
Huh.
Or maybe just the power rule. I don't know.
Oh.
It's probably power rule. Anyway, there's a button in your calculator, not a button, it's an option in your calculator, that says, what's the probability, how many different ways could you arrange these 3 books?
There's 3.
How many ways can you arrange these 5 books differently?
NCR.
So that would be 5, see I can count, 5, choose, how many different combinations of 2
5.
books are there?
Fine, 2. 5, 2.
So
2.
Sorry.
2.
I haven't thought this through. Sorry. Well, we'll start with 1. If there's 5 books, how many different ways can you select 1 book? Well, there's this one.
There's this one.
And another one.
yeah.
5.
So it's going to be 5, choose 1, 5th row, 0 value, first value. How many ways are there to select 2 books? So you could have
10.
this 2, and 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 this 2, I think. I don't remember how.
Yeah, there's a bunch of different ways.
Right. But distinct combinations.
Oh hey, my battery fell out on my phone.
Distinct combinations where the order doesn't matter. There's going to be 10. How about 3? There's going to be 10.
You know how tempting it was to get that sad attempt at getting it like on video? That was okay. Sorry, YouTube. We'll have to explain later.
He dropped his phone. Okay. So 5, choose 4 is this. Anyway, the whole thing is that you can use Pascal's triangle to find the the combinations of different ways you can arrange something, which is very helpful in probability. You can actually find out what's your chances of getting a full house in... I'm so ignorant about poker. What's the best thing for poker?
Oh, it's a royal flush.
Royal flush. We can calculate your chances of getting a royal flush using those. Granted, you'll have to go down to the 52nd row, but...
Yeah. Let's
No
not.
big deal.
Let's not and say we did.
Just add it
Now, where does 5 show up?
on the diagonals.
It does show up on the diagonals, you're right. So, if we go this diagonal, which is just 1, and you add it, it's going to be 1. This is 2. Is that right?
No.
Yeah, it is.
Is it?
Oh,
It's
okay.
3.
Yeah. No.
Wait.
Yeah. Yeah, it is. Yeah.
And then
That's 5. Yep. Okay.
5.
Starting to make sense.
And then this isn't very well drawn, sorry guys.
That's all right.
It's 9.
4, 3,
That's 8.
8. And you see the word Fibonacci comes back into this. So, I don't know if Pascal was just doodling around or whatever, but he ended up finding something that has lots of random things that are really helpful. So, just like Weihart says, keep doodling in math class and see what happens. Maybe you'll discover something really meaningful.
Maybe you'll invent something in math.
Yeah, maybe.
That's all I got.